Hello everyone, how is your studies going on? I have completed uh, two chapters or maybe three chapters of the linear algebra, and I'm understanding it. I have been having a hard time understanding the theorems and trying to prove it by my own. So I'm taking a very long time. I'm spending a lot of times just to understand those theorems. So today, now one of the chapters that involve very important theorems and is very important from the perspective of examination is matrix operations. And I'm having a hard time understanding this chapter. So even though it's very simple for some of you, it might be simple for some of you, but let's see and let's try to understand it together. Okay, so matrix operations. We have matrix addition and matrix subtraction, and we have some laws for scalar multiplication. I am following Heritage Publishers book, or textbook of linear algebra, BA BSc second year, and I'm seeing it. Yes, so let's talk about matrix addition and scalar multiplication. We can think of a matrix in the form of columns, column vectors, right? So if we have, let's suppose, okay, so let's say we have a matrix A which is denoted by Aij. Similarly, we have B which is denoted by Bij. These two matrices are the same order, M and N. So the order of these are M cross N, and they are said to be conformable for addition if the sum A plus B also have the same order. It is true. Now we can write these as A plus B is equal to Aij plus Bij, right? And this is going to give us Aij plus Bij, and if I say these to be a new quantity Cij, it must be of the same order. Now if we talk about the subtraction, then it is also the same thing, but we have a minus sign here, and this gives us minus sign here, and let's suppose this to be D, and this must also be of the same order. So this is about the matrix multiplication. Matrix addition. Now let's talk about matrix scalar multiplication. So there are some laws of this, and the first law says that if we have two matrices A and B again, then, and let's suppose that K and T be some scalars, then K times T of A is equal to K times T of A or T times K of A, and this is called as associative law for the scalars. Okay, this is called associative law. Associative law for scalars. Let's suppose we have addition of these two scalars, then we can write Ka plus Ta, which is called the distributive law of scalars. Similarly, if we have K but we have two vectors now, then we distribute the scalar with the matrices. So it's called the distributive law of matrix addition. So it's a distributive law of matrix addition. I'm not going to write it all because you also have the book. I suppose it will be easier for you to look at that. Now again, we have identity. So if we have identity matrix A, if we have identity matrix I and we multiply it with A, then it is also equal to A. Okay, sorry for the disturbance. And let's suppose if we have a K and we multiply it with a minus A, that means the same as if a matrix A is multiplied by a scalar minus K. Okay, so this is also a law, and there is something called additive inverse. And additive inverse means if you have a matrix A and you add it with the inverse of the same thing, then it is going to give us 0. This is called additive inverse. Is it? Let me check. I think so, yeah. So we can say minus A is the additive inverse of A. So let's not waste our time in these things. Let's directly talk about matrix multiplication. Matrix multiplication. Up to now we have seen, if you just follow the sequence of the book, up to now we have seen the multiplication in between vectors and matrices, but now on we are going to see matrix multiplication. Matrix on matrix multiplication. Let's suppose A is a matrix B1 C1 A2 B2 C2 A2 A3 B3 C3, and let's suppose B is P1 P2 Q1 Q2 R1 R2, and if we have these two matrices, the product AB is gonna be what? You first of all, before writing that, let's see what is the order of this matrix, order of the matrix after multiplication, and also matrix multiplication doesn't exist for every matrices. We have to see the number of rows and number of columns. If the number of columns of the first matrix is equal to the number of rows of the second matrix, then only the matrix multiplication is viable. So if you see here, it's a 3 into 3 matrix, it's a 3 into 2 matrix, right, yes, then it means matrix multiplication exists such that the resultant matrix is going to be of order 3 times 2, 3 by 2. So 3 by 2 means 1, 2, 3, 1, 2. Let's see. So we have this to be A1, B1, A2, A1, B1, B1, Q1, and C1, R1. Then after A1, B2 plus B1, Q2 plus C1, R2. Then after A2, B1 plus B2, Q1 plus C2, R1. A2, B2 plus B2, Q2 plus C2, R2. This sounds cute, doesn't it? So now then A3, B1, B3, Q1 plus C3, R1, A3, B2, B3, Q2 plus C3, R2. This is our matrix. Now if you see this, you can think of it as this. What is this? So let's suppose this to be P1 vector. Let's suppose this to be Q1 vector. If we say that, and let's suppose this to be what? This to be what? Maybe A1 vector transpose B1. Then let's suppose this to be A2 vector transpose. Let's suppose this to be A3 vector transpose. Then we can write AB in the form of the linear combinations, right? So linear combination of that can be written as maybe this. Can we write it in this form? A1 transpose times B1 transpose. This means we have A1 B1 C1 times P1 transpose. Okay, transpose means A1 B1 C1. Oh, wait a second. Transpose, yeah, okay. Q1 R1. This is gonna give us A1 P1 plus. Yes, we can write that. So that means we're gonna get what? So this becomes A1 transpose of P1 vector, A2 transpose times P2 vector, and A3 transpose dot P3 vector. We can write it in this form. So we can write the matrix in this condensed form too. Okay. So from this, what can we conclude from the conclude in general? So in general, we can say we can write the matrix in terms of linear combination. In linear, you may ask linear combination of what? So linear combination of the rows and columns. Okay, so let me check. So if we have two matrices, you can check the book. If we have two matrices A and B, and we want to multiply them such that, let's suppose the elements that we get, let's suppose these to be C1, whole thing to be C2, and so on, then we can write it in the form such that Cij of each of these elements of the matrix can be written in general as Cij equals AI1 B1j plus AI2 B2j plus that up to AIP BJ BQJ. Okay, and this as a whole can be written as K goes to 1 to P, and that's gonna be AI K B KJ. Okay, actually this is a P and makes sense. So thing that we have as a component or as an element of matrix can be written in the form of this. Every single component. So if I say C11, that means the first row and first the position corresponding to the first row and first column. If I say 33, this means the element of the matrix which correspond to the third row and third column in this way. Alright, so this is how we do things, and we represent things. Yeah, we represent things in matrix. Okay, now after understanding this, we have also come to the fact that we can do matrix multiplication by two ways. First one is you can break break the columns of the second matrix and write them in the form of vectors. Or second way is that you break the rows of the matrix, first matrix, and you can do that matrix multiplication. So it turns out that these two processes have two different names, One is called pre-multiplication and one is called post-multiplication. So let's see those. So pre-multiplication. When we talk about the product of the product of the matrices A and B, it is important to remember that AB and BA are usually not the same. Consequently, it is common to use the terms pre-multiplication, left multiply, or in front of or pre, and post multiplication, right multiply, or after a post. When we say A is post multiples by B and B is multiplied by A, it is referring to the product AB. It means that, let me write it, A is post multiplies by B, or B is pre multiplied by A. This means AB. And if we say B is post multiplied by A, or A is pre-multiplied by B, that means BA. That means if we see this, the post multiplies by B, that means A is already there and B post multiplies it from the right hand side. Similarly, if we have B is the post multiplied by A, that means B is already there and A multiplies it after by the right hand side. So this is what, so whenever we say post multiplies, just remember that it always multiplies by the right side. Similarly, if we say pre, then the A is already there, B multiplies it by left hand side, and similarly there is B is already there and A multiplies B by the left hand side. Just a saying, okay, it's just a way of saying it. So let's see two examples, one by one for the post multiplication and one for the pre multiplication. If we have A, let's suppose we have A which is given by 3, 2, 1, 4, 0, minus 1, and let's suppose B is 1, 3 and 2, 1, and let's say we multiply this by post multiplication. Post multiplication. What do you think I am referring here? So let's suppose we say B post multiplies A. If I write this statement, what does it mean? It means that A is already there, B multiplied it by right hand side. That means we need to find out AB. I'm not going to do that. You know how to do it. And again, if I say same thing, let's suppose this to be pre-multiplication. Let's suppose our question says us find the pre-multiplication. Then that means pre-multiplication with respect to what? If that is not defined, then we can say pre-multiplication. So let's suppose B A pre-multiplies B. That means that B was already there, A comes from the left hand side and multiplies it. Again, we have to find out AB. Okay, let's not waste our time here and let's go directly to the dot products. Now, what do you mean by dot product? If you have already seen dot product closely enough, you would remember that it looks very similar to the linear combination. And that is the exact thing that I am going to discuss now. So we have x equals, let's suppose we have n components in x. Let's suppose we have y, and again y also has n components, then the dot product in between them is denoted by what? This times this, x1 times x2, sorry, y1 plus x2 times y2 plus dot 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 up to xn times 2yn, right? We can write it in the form of summation I equals 1 to n xi yi, and this is x dot the dots seem to be very large, so x dot product y is actually just the linear combination in between them. Okay, actually this is a very small part, or we can say it's a subset, or it's a version of something large which is defined as an inner product. So we can say the dot product is inner product, but in the case of two dimensions, when we have two dimensions. Now you may be wondering one thing. I have seen this confusion very in many people, and actually I also had that confusion. And the confusion that I'm talking about is that if we have x, let's suppose a vector, and y, suppose a vector. Let's suppose now I am saying that these two belongs to R2. Okay? Yeah. So let's suppose I say these both lies in second dimension. Now you may be wondering, alright, but it has n components, right? So it has n components, but how can it be in the second dimension? Now the answer to that is, wait a second, okay, let me think about it. Actually it is not a very good example to show that. Actually it here, here it is, it belongs to Rn, but let's suppose we have a vector v, okay, and v has v1, v2 up to vp components, and I say that it belongs to Rn. Now it doesn't mean the p and n are same, because when I say v is a vector space, has these many component and this many component, that means that the number of components in the vector space is p, but each of these p has n component, and that is what determines the Rn. Rn means how many components does that V have, individual V in the vector space have, that determines Rn or Rm or anything. So the number of dimensions are actually mentioned, are determined by the number of components in each of these vectors. So if I say x, and x has x1 and x2, and y has y1 and y2, that determines these are in R2. Okay. Now if I say this to be a vector space and these to be some vectors, and if it has again x11, x12 and x13, three component, then I would say even though the number of vectors in the vector space is 2, the dimensions it follows is 3. I think that makes sense. Okay, I'm not going to waste further time on that. Let's directly see this dot product. So we can write dot product in this way. We can use the denotation notation when we can say A, B, I, J is the dot product of row I in A with column J in B Let's use an I to designate row I in A. So what does it mean? Alright, so we have, so I think it wants to introduce some new notations. So let me check it, okay? I'll say it. So yes, uh, we up to now we have seen the dot product looks like that, and the matrix multiplication looks like this. Actually, it's just a component of matrix multiplication. Okay, each of the component of the matrix multiplication looks like this. Looks like this. Similarly, if we just see this matrix multiplication in the form of dot product, then we can just imagine a single row of a matrix and a single element of the column column, or we can say the vector b. Just let's suppose this to be let's suppose the element to be bj. Then that we can think of it in form of dot product, and so a b I z. That means the ith component of the matrix formed by the multiple of a and b is a dot product of row I in A with column j in B. That means if you so let's suppose I think I should write an example of it, and so it will be more clear. So I'm not going to erase it, and I'm going to give you an example. So let's take a rather simple example. Let's suppose we have A to be 2 into 2 matrix. So this will be 2, 2, 3, 4. Let's suppose B to be what? Let's suppose this to be also a what? Also a what? We can think of it as B2 all the way to BZ. So let's suppose this to be 2, 3, 4, 5 also. Okay. Then matrix multiplication AB is going to be what? This times this gives us 2 times 2 plus 2 times 4. This times this is going to give us 2 times 3 plus 2 times 5. This times this is going to be 3 times 2 plus 4 times 4. And this time this is going to be 3 times 3 plus 4 times 5. What is the result? It is 4, 8, 12, 6, 10, 16, 6, 8, 14, 9, and 20, 29. Now we have A, B, and if you see the denotation or notation of, I don't know why I always say denotation, but rather I should say notation. So let's suppose the notation of each of these places be A11, A12, A22, A23. Alright, sorry, A21 and A22. Then what is the component A11? That is 1, 2. A1 2 is 16, A21 is 14, A22 is 29. Now let's see this. Sorry, not this one, but maybe this one. Yeah, this statement. Let's see the correctness of this statement. So to check that authenticity of that statement, we need to see what it says. It says a dot product of row I in A with column J. So for example, let's see A I. That means we are talking about matrix. So we are talking about this is given by matrix multiplication in between AB, and we were talking about Ij, and so that I equals 1, 1. That means what is the row? Ith row. Ith row of 1. Sorry, ith row of A. What is ith row of A? Sorry, not ith row, but 1, first row. First row is this. It's the first row. So where I is equals to 1, it's a first column where J is equals to 1. So we can think of that as 2 times 2 times 2 times 4. Right? So we can think of it as let's consider this to be x, consider this to be j, We can think of this as x1 y1 plus x2 y2. That is going to give us 2 times 2 plus 2 times 4, 4 plus 8, 12, exactly the same thing. That means it is true that we can write it in this form. We can write, or we can say, we can denote, we can find out, locate any component of the matrix. If we have a large matrix, let's suppose we have a n by n matrix, and we want to find out the matrix multiplication in the component after the matrix multiplication. Let's suppose m in n. Then we don't have to perform all the matrix multiplication. We can just find out this component by finding out the nth row of A and nth column of B, and multiplying this by following the method of dot product, and we can find out the value. So it's a very time saving thing. Okay, and we have a theorem following it. Let's see that. This is the theorem. Theorem says the ith component in the product of the two matrices A and B can be written in the summation notation or as the dot product of the row I in A with column J in B, just like that. Now proof of it is this. I considered A and B both to be mn matrices, or the matrices with the order m by n. Then I considered the A to be a row and B to be I chose a row of A and a column of B, and I wanted to show that these matrix multiplication can be shown in form of dot product. So I wrote that dot product, and we can denote that by this way. So which proves the theorem. Okay, now it is a very powerful theorem, but I don't want to repeat it again and again and make it a boring thing. So let's see a last example, and I'm not going to talk about it. Okay, this is a question. What is the third, or we can say 3-tooth element in the product of a matrix? A and B, we have matrix product, and we have to find the product of the matrix, and we have to find out the 3-tooth component or element. Now for a ordinary person, it seems very difficult or very tedious, because we have to find out the product of this whole matrix. But from this theorem, we can just say that 3-tooth component is just the dot product of third row and what? Second column. What is third row? 1, 2, 3. This is the third row. What is the second column? This is the second column. So multiply it. Not multiply it, but dot product it. It's gonna give us this. This. Now what? Minus 35. This becomes 30, 40, 50. Minus 50. Minus 7 plus 5. Maybe minus 52. Please check the calculation, and I think this is true. Okay. Now this is it. I'm not going to talk about it from now on, but I will use it whole chapter. Okay. So now what are the let's talk about special matrices. What are special matrices? Now we already know about some of the matrices, such as square matrices, diagonal matrices, identity matrices. Okay, so identity matrix has some important property here. Not an important property, but you can find it out if you have seen identity matrix. So if we say identity matrix, which looks something like this: 1, 1, 1, 1 in the diagonals, 0 on the other places. This is an identity matrix. If you see this, you can write an argument that where I is equals to 0, the element, I can say element ij is 1. When I is not equals to j, I the element is 0. This is called Kronecker delta way of writing it. Okay, so if you see this, it's what? It is A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, A44. I just wrote the positions of these elements. So if you see, if I consider A, Ij, and I am saying that if A I is equals to j, then only it is 1. Let's check that. Yes, it's true. 2, 2, it's true. 3, 3, it's true. 4, 4, it's true. Others are not equal to each other, so others are 0. So this thing that I have said by using Kronecker delta seems to be true. Okay. Now let's see a theorem. For any n cross n matrix A, we have In A equals AIN equals A. Says that if we have any n cross n matrix and we have INA equals AIN equals A. Can you prove this? Now if you can take a whole matrix as a whole of m cross n, and you can use that, but there is a very elegant way to prove it by using the method of dot product. What you can do is you can find out ith component of this matrix multiplication is Ri and Bj, right? You can do that. Now this is equal to just because of the thing that I just erased, I'm sorry for that. It equals to summation what? A I K B A J. K goes from 1 to n. Because of this thing, what we can say is, okay, so yeah, we have that, right? And we know this, yeah, we know this by the theorem. Now we also know that now the matrix that is multiplying A is not a simple matrix, it's an identity matrix. So it's a matrix which becomes 0 when I is not equals to j, and it becomes 1 when I is equals to j. That means we need to account that Kronecker delta function. So for accounting that Kronecker delta function, we can write it as delta of kj. And when I say delta of kj, that means when k is equals to j, then only we can write it as 1. Otherwise it's 0. That means that if we have, okay, so that means that this is nothing here. That means it doesn't have any impact here, or we can say everything is controlled by this. What is a better way to say it? Let me check. Yeah, so this is a better way to say it. So we have this, right? Now you can think of this as a dot product in between this any row of a matrix A and any column of this identity matrix. So if you see this multiplication, if you multiply this whole thing, or you can, if you want to find the dot product in between this whole thing and this, or any of these columns of identity matrix, you are just going to get one of the element, either first, second, third, fourth, or any of these, because all the other terms would be zero. Because of that, every single time you will get AI1, AI2, AIN, so we can say you get AIZ component only. And this is why I can just say that A times I is equals to I times A equals A. This is a proof, okay? Now we are interested in understanding upper and lower triangular matrices. And we have a lot of theorems about this, and these are very important for examinations also. It's a very long chapter, but I will try to complete it. So let's see the triangular matrices. We have two types of triangular matrices, as you know, upper triangular and lower triangular. And I think you all know that upper triangular means it makes a triangle on the upper side of this matrix, and lower triangular means it makes a triangle on the lower side of the matrix. And now it turns out that every single time if you want to write the triangular matrix, upper or lower, you don't have to make this whole thing every single time. We have a Kronecker delta, not Kronecker delta, but a function, a way to write this in this form, okay? And it says that if it's a lower triangular matrix, then it becomes the case. That means it becomes 0 if I is smaller than j, and it exists if I is either equal to j or greater than I is greater than j. Similarly, for upper triangular, lower triangular. For upper triangular, if I is greater than j, it is 0, and if I is smaller than or equals to j, then it exists. You can check that, okay? But I'm going to go to the next topic. It turns out that we have two theorems related to the triangular matrices. First one is the addition of the two triangular matrices of the same order gives us a triangular matrix, which is a very obvious thing to do, obvious thing to be, so you can check it by own yourself. Now there is another theorem that I want to prove, and that is the product of the two upper triangular matrices of the same size is also upper triangular matrix. And again, it seems seems trivial, but let's see that, okay? Maybe we find some interesting thing. So let's see this thing. The theorem says the product of the two upper triangular matrices of the same size is also upper triangular matrix. And okay, so we have two upper triangular matrices. Wait a second. Let me check the theorem.